All right, so we got chapter 18 of your memoirs right now. We're going to look at the respiratory system here. So looking inside of that, we're going to be looking today at the structure of your respiratory system. So, obviously we'll talk about the lungs and stuff, but there's a lot of other structures that are part of the whole system there as well. Everything from like, your nose and mouth and stuff. Then we'll talk a little bit about like what we mean when we say respiration, like gas exchange versus gas transport. We'll look at very slightly, we'll look at some of the disorders, but honestly, we'll probably move through those pretty quickly, and aging, and then all the special equipment and stuff. We're not going to spend too much time on that. So, looking at the idea of respiration, right? If we're looking at the respiratory system, by definition, we're going to call this the system of the body responsible for proper cellular functioning, which is kind of a funny definition, right? Like you would think that the definition would be like, isn't it the system that extracts oxygen? It's like, well, I mean, that's the whole purpose we extract oxygen, right? Like this is all about ensuring that your cells can breathe. And your cells performing respiration, which we call cellular respiration, is the number one thing that kind of gives us life here. So we definitely need to make sure that we have our respiratory system effectively bringing in O2 molecules to ensure for proper cellular functioning. So this is the system of the body that is responsible for extracting oxygen from the environment so that it can be utilized and transported by our body's cells. So when we talk about respiration, at its most basic, we're talking about breathing. But breathing and respiration are slightly different. Like if we think about this from a different perspective, it's almost like we want to relabel it in our brains. We want to call breathing ventilation, and we want to call the process of like bringing oxygen into our cells, that's what we want to call respiration. So there's a slight difference there, right? Respiration and ventilation are ever so like ventilation is about bringing air into your lungs. Respiration is about getting oxygen into your bloodstream, because air is actually mostly nitrogen. Like for the record, if you look at like the composition of air, we think of it's like it's all oxygen. It's not. It's actually mostly nitrogen. You can see most of what we inhale, 78% of the gases that you breathe in is nitrogen. Only about 20% of it is actually oxygen. Then there's a bunch of other gases and stuff in there as well. So ventilation is bringing gas into our lungs. Respiration is allowing oxygen to pass into our bloodstream, or allowing oxygen to pass into our body's cells. So a little bit of a different definition there, right? And that's why this is the process of obtaining oxygen from the environment and delivering it to our cells. It ensures proper cellular functioning. So the phases of respiration, if we look at this, right, and we talk about like what, in the same way that we looked at blood, and blood flow during the heart yesterday, we've got systole and diastole, which is what's pumping blood or sucking blood into the heart, right? But we've also got, like, if we look at ventilation here, there's 4 distinct phases here. So there is pulmonary ventilation. And again, ventilation is the process of bringing gas into the lungs, right? So we're going to define pulmonary ventilation as the process of driving massive amounts of gas into the lungs. Okay, so we're bringing this bulk flow of gases, but we only want the oxygen, right? We don't want any of the nitrogen or argon or any of the other stuff. So what we're going to experience is we're going to experience external gas exchange, is what we call it. So we call it external gas exchange, even though it is taking place inside your lungs, because technically this is an external to internal situation, right? Remember when we talked about the digestive system, we talked about the human donut thing, right? Technically, when food is sitting inside of your stomach, it's not actually in your body yet. It's still technically outside of your body, because donut, right? Like, yeah, it's in the donut hole, but it's not in the donut body, right? Same thing is true of our respiratory system. You may be driving air into your lungs, but like I could thread a wire or a tube or whatever into your lungs, which means that, like, since that can go in and out, like I can't drive a wire through your skin without like puncturing you. That doesn't count. But like this is, again, like an uninterrupted tube. So you are basically bringing oxygen into, the outside environment where it can diffuse into your bloodstream, and then it diffuses into the inside environment. So we call that external gas exchange because it's an external place where it's happening. And this is the process of driving oxygen into our red blood cells while driving carbon dioxide out of our red blood cells. So carbon dioxide is going to leave the body and enter the lungs. Oxygen is going to leave the lungs and enter the body, right? Then we have gas transport. And gas transport is basically your red blood cells carrying stuff around, right? So if we are, putting an oxygen molecule onto a red blood cell, and then that red blood cell is traveling to a body's tissue to drop it off, that is gas transport. Now we also have your internal gas exchange. Once we have the transportation, now we're going to experience like your cells doing the same thing that your lungs did, where your cells are going to uptake that oxygen. And they're going to do the exact reverse process of external gas exchange. They are going to bring in oxygen and spit out CO2. So this is the process of driving oxygen out of the blood cells into the tissues and CO2 out of the tissues into the red blood cells. So that is how, we are experiencing ventilation. Then what will happen is, this whole process will kind of reverse, right? So it'll go, you'll have, let's say it's a new oxygen molecule, right? And so it gets sucked into your lungs and experiences pulmonary ventilation. Then that oxygen molecule is going to pass into your red blood cells and experience external gas exchange. Then that is going to be carried by that red blood cell to whatever tissue it happens to be going through. We call that gas transport. Then that oxygen is going to get sucked out of your blood cell into some other type of tissue in your body. Let's say it's your quadriceps muscle, right? And so it gets sucked out of the red blood cell into the quadriceps muscle, and it gets swapped out for carbon dioxide. Now, carbon dioxide is going to work its way through gas transport back to the lungs, and it's going to experience external gas exchange, where the carbon dioxide will leave the blood cell and get traded for a new oxygen molecule. And then you will experience the reverse of pulmonary ventilation, where you exhale and you're going to get rid of all that CO2. Does that make sense, guys? Pretty good on that? All right. So that is, that's respiration in a nutshell, right? Which is, again, different than just breathing. It is breathing on a cellular level. So here's where that's happening, right? Again, we experience external gas exchange at the lungs. It goes to whatever, tissue it's going to, and then becomes deoxygenated. Then it transports back to the heart, gets pushed over to the lungs, spits out the CO2, gets reoxygenated, and then goes to whatever tissue of the body it happens to be going to. So that's where we are constantly doing this, right? This is our entire process of respiration, which is different from ventilation. Now you have to have all these specialized materials to allow this to happen. We need to be able to make our external environment available. We have to make our internal environment be able to extract oxygen from the outside environment. And so because of that, we have all of our respiratory passageways, okay? So when we look at the structures of your respiratory system, we've got this structure that conducts air into our lungs. Those are going to be like your actual lungs themselves, and then like the diaphragm, which creates pressure gradients to draw air into and out of the lungs. And then we're also going to have things like your nasal cavities, your pharynx, larynx, your trachea, which is this cartilage tube that is, bendy and flexible so that it doesn't ever, it stays open, but it can also like move pretty freely. The lungs themselves, and then there's going to be some pleural linings there as well. So if we look at, whoops, I just closed my PowerPoint. If you look at this, sorry. You can see the different structures here, right? So you've got your larynx, which is like your mouth coming in. You've got your pharynx, which is like your nose coming in. All that's going to be tied together, and then it's going to travel down into your trachea, which is, this really bendy but still relatively solid open tube. And then the trachea is going to split and go into your lungs. It's going to divide into what we call your bronchi. Okay, so you've got your left and your right bronchi here. And then your bronchi are going to branch down into smaller and smaller and smaller branches until eventually they become what are called bronchioles. Similar to how we talked about how arteries are really large and arterioles are basically small versions or small branches. Similar with the bronchi situation, right? They're named after the same sort of design there. And so your bronchioles are going to divide smaller and smaller and smaller, okay? So your bronchi are the two primary passageways that divide and branch off into each lung, and then they further divide into your bronchioles. And then the bronchioles are the small branches from those primary bronchi. These will eventually end in what are called alveoli, okay, which are these little popcorn-shaped sacs that we'll look at in just a second. And there's some other specialized materials in the nose as well. You get your nasal cavities, which have all this like mucous membranes because they're constantly creating snot, which is a really good thing. We love snot. That allows us to warm and moisten the air as it's traveling into our lungs, which makes it easier to diffuse later. You get your pharynx as well, little portions of the respiratory tract that's like about to divide into like the difference between your esophagus and trachea. Your larynx, right, which is this cartilage framework. You're going to see like there's your Adam's apple, for instance. It's going to be located on that. You'll have your glottis and your epiglottis, which are actually there to basically divide all this. And so there's this little bone that kind of keeps the hole open. And then you've got your epiglottis, which, we want our lungs to be open all the time, but the epiglottis is there to basically be this little flap that closes over our lungs to allow food, which shares this common tube, to go into our esophagus instead. So that's going to go down, into your digestive system rather than going into your lungs. So the lungs are actually always open. And then the second you swallow food, this closes down like that and allows food to travel that way. You can see here's your vocal cords, which are going to vibrate to make your voice and stuff. But the trachea is this big, cartilage framework that allows that to travel there. Again, special structures. We're not going to spend too much time looking at those. We move through that pretty quick. Our concern, what we want to look at is the anatomy of how we conduct oxygen in here. And so that's why we have those bronchi, those passageways that branch into each lungs, and then each lung, and then those end in those little bronchioles. So your bronchioles they kind of look like these little trees. When you look at your lungs, you can see they branch off and then they're filled with these, crazy big branches. They get smaller and smaller and smaller and smaller until eventually they end in these little microscopic blood vessels that we call alveoli, okay? Not blood vessels, sorry, microscopic little sacs that are covered in blood vessels. So they branch and then they get smaller and smaller and smaller. And then they end in these little these little alveoli here, right? And take a look, you can see, look at how covered these tissues are, these little popcorn shaped thingies. They kind of look like popcorn mixed with like ginger, but they're just covered in blood vessels. And that right there is what allows oxygen to actually move into our bloodstream. So when you look at like a smoker's lung, the reason smoking is so bad for us, other than just all the chemicals and stuff that have like really bad cellular effects, you'll notice, look at how fewer branches there are in this, right? Compared to like what you see here, which is this big, healthy, lots and lots and lots of branches. So what smoking does is, you got to remember that, like, a lot of people think that like when they smoke, stuff goes into their lungs and they exhale and they see the stuff come out of their lungs, right? You see the smoke come out of your lungs. And so you would think that like all of it's leaving, but you are putting that all those little particles, all that smoke is made up of all these little tiny itty bitty particles of stuff. And you're putting all that stuff into your lungs and it's a wet, sticky environment. So a lot of it ends up staying in there and it gets stuck in there. And that's where you get like what's called tar. And tar basically starts covering these sacs. And so when you look at like tar, let's see, actually, bronchioles covered in tar. Yeah, I mean, that works, I guess. really want like a real sludge looking picture. I guess this works. So you can see what'll happen is like they literally get covered up by stuff, right? So what ends up happening when your alveoli are covered in stuff is they can't diffuse oxygen effectively, right? These little blood vessels are all covered up with like little particles of things. They're just covering it, right? There's just sludge covering the whole thing. Same thing with bronchitis or emphysema. You know, it's the same situation. It's just there's other stuff covering them. This is why really nothing should go into your lungs. You know, this is why, and I've said this before, like, you know, I'm not a fan of any version of smoking. You know, smoking really just, there's no version of it that's actually that good for you. And I know that like there are some really positive effects to cannabis and stuff. It has really positive effects sometimes in the human body. I'm not saying that like cannabinoids are unhealthy for you, but smoking them is just not a very good vehicle to get into your body, and it can cause a lot of, you know, problems. Same thing with vaping. Vaping does the exact same thing. You know, put stuff into your, don't put stuff in your lungs. You know, like if I were to smoke broccoli is incredibly good for you. You know, shouldn't smoke it. Like, don't put it into your lungs, little particles of stuff. So what ends up happening is you have this like major amounts of surface area, but then, you know, if imagine how much pressure something like this creates, you know, when you have like all this gas, like imagine, you know, you have like a series of paper sacks, right? And one of those paper sacks is no longer flexible. And so when you push a massive amount of air in there, what's going to happen? The walls of that sac are going to pop. They're going to tear. So what you end up with is what looks like this. This is an alveoli that is experiencing basically emphysema, where the walls have all been broken down. And because there's no, you know, it's just one big wall. And the reason that's bad for us is because this has a greater amount of surface area. And because it has more surface area, it can diffuse more oxygen molecules. So what I mean by that, right? I'm going to pull up sort of Microsoft Paint here, but like, you know, if I asked you to paint these 4 walls of this square, you know, it would take you however long, take however much units of paint, right? It's got plenty of surface area, but if I were to draw exactly the same thing, I'm going to draw, you know, let's go like this. This is going to be the same size in terms of like the overall big square, right? But now what I've done by having like 4, you know, slightly smaller squares, you know, this is about the same size. So the outer surface area is the same, but now you have to paint between these little cracks here, which means that we just increased the surface area massively. There's way more surface area in this version. In fact, I'm supposed to know this. It's like I think we quadrupled it or doubled it, whatever. But if I were then to go, you know, imagine if we did, you know, something like this, right? And then just because I'm going to make my life easier, I'm going to the outer part of this square is the same, right? Like, so now this has the least amount of surface area, you know, just this outside bit here. This has the second most because now it's got the outside bit of all of these. And this has massive amounts of surface area. So that's why our lungs branch smaller and smaller and smaller and smaller and smaller. What that does is that maximizes the surface area. The amount of paint that it would take to paint this is way less than the amount of paint that it would take to paint something like this. So by doing that, we are maximizing surface area. This structure gives us the ability to inhale trillions of oxygen molecules every single day. But if we were to cover up some of that surface area with tar, and then we are still bringing in massive amounts of gas, that gas may burst the walls of some of our blood vessels. And so what ends up happening is you tear the walls and you are left with less surface area. You may still have blood vessels there, but you don't have as much surface area. And without that surface area, you cannot bring as much oxygen into the body. And that is why, you'll see people who have emphysema. They need to like have, oxygen tanks that they need to breathe into, because that is, making it easier for them to get oxygen into their body. So remember the anatomy here, right? The bronchi are the primary tubes. They branch into bronchioles, and the bronchioles end in the alveoli, right? And the alveoli are what are covered in capillary beds. That is where the oxygen exchange is taking place. And then there's also some connective tissue that covers your lungs, which we call your pleura. And your pleura is basically like kind of similar to like you've got you remember we talked about the pericardium, and it's this like sac that holds your heart in place. And it's got this like fluid lining between it that keeps it really like, slick. Well, that's kind of what your pleura is. Your pleura is basically this outer lining. I think we saw a picture of it. Yeah, you can kind of see there's a little bit of space between the outside of the lung. And again, that's just really slick to make sure that it's easy for your lungs to be able to expand and contract. Because we've got this respiratory pump here that we're going to talk about that is responsible for expanding and contracting the lungs, and that creates pressure gradients. So let's take a look at the processes of respiration here, right? So if we're talking about like respiration, we're talking about like, exchanging things. First, it's going to start with ventilation. Ventilation is just bringing in a massive amount of gas into the lungs. Then those gases are going to be exchanged. You're going to drop off CO2 into the lungs, and you're going to pick up oxygen from the lungs. Then those gases are going to be transported to whatever body tissues they're going to. And again, we're going to see gas exchange. It's just going to be the exact reverse, right? Your blood cell is going to drop off oxygen and pick up CO2. And again, it'll then be transported, it'll exchange, and the process will repeat. So when we look at pulmonary ventilation, we got to talk about the difference between inhalation versus exhalation. And that's all being done by your respiratory pump. So all of this was your respiratory passageways, right? These passageways that allow bulk flow of air to be able to travel. But we also have to have a pump that creates pressure gradients in order to draw that air into and out of the lungs, right? So when we look at the idea of like your respiratory pump, it's all under the control of your diaphragm. Your diaphragm is this dome-shaped muscle that when it contracts, it actually flattens down like this, and that drives air into and out of your lungs, right? So we look at like the diaphragm. You can see it actually sits in this kind of dome shape. There we go. It sits in this little dome shape like this when it's relaxed. And so in this relaxed position, it's kind of it's up like this. And then when it contracts, rather than like pulling together the way like a traditional muscle pulls together, instead your diaphragm flattens down like this. And so it will pull this way. And what that does is it's like you grabbing a sack and pulling that sack open, right? That draws air into the sack. Well, the same thing happens here. Your diaphragm flattens down, and that drives air into your lungs. So that is the process of ventilation. And then when you relax the diaphragm and it relaxes and goes back into its dome shape, that pushes the air out of your lungs. So inhalation, which we sometimes call inspiration, is the active phase of breathing where we are contracting our diaphragm to draw air into our lungs, right? Exhalation, which we sometimes call expiration, is the passive phase of breathing, which involves driving air out of the lungs because your diaphragm is relaxing back into place. So the diaphragm relaxes back into its dome position, which, now there is more pressure in your lungs than there is in the atmosphere. So the air is going to go wherever the pressure is the lowest, just like your heart, right? So again, here we can kind of see that, right? And there's other things as well that are helping this. It's not just your diaphragm. You can see in the picture here, we've got like what are called your intercostal muscles, which are all these little muscles that live between your rib cage. They're going to help with this process as well by lifting up the ribs and stuff. But primarily, the big one we want to talk about is the diaphragm, right? The diaphragm either relaxes back up, which draws air out of your lungs, or it contracts down to draw air into your lungs. And here we can see like the pressure of like, after a while, there's going to be, a massive amount of pressure because the lungs can only expand so much, which is going to naturally want to drive that air out of the lungs, which is why you can breathe while you're sleeping, pretty easily, because a lot of that is very, very, very passive. It doesn't take very much to contract your muscles because there's nothing really pushing too hard against them while you're asleep. And so breathing is a very, very passive thing that happens autonomically. But if you look at like, people who have like sleep apnea, where maybe their chest is really heavy because they have excessive body weight or, certain hormonal disorders and stuff, what'll happen is their muscles will not, contract hard enough, and then air won't get drawn into the lungs. And the body's like, hey, we're not getting any oxygen. And then all of a sudden it wakes up and does this massive inhale, like, right? And it can be very disruptive to our sleep, which is one of our problems that is associated with obesity. So any questions about inspiration versus expiration, guys? Any questions about like drawing air into and out of the lungs? Feeling good on that? All right, well, let's take a look at our lung volumes here. So we need to have like a measurement for how much air is being drawn into and out of the lungs. And so we have different like terms for the different volumes of our lungs. So we've got what is called tidal volume. Tidal volume is the amount of air moved into and out of the lungs during normal breathing. So you guys are all, unless one of you is, I can't see anybody, but if any of you are like physically working right now, lifting stuff, or if you're on a treadmill listening to me right now, if anybody's doing that, well, then maybe not your tidal volume. But if you're sitting down and you're kind of relaxing, you are using what we call your tidal volume. It's normal, quiet breathing, it's the normal breathing you do most of the day, unless you're exercising. But then there is also, we call it the tidal volume because it's like the tide, like in and out, it's very relaxing. Then we do have like a little bit of volume beyond that though, right? Like if I did like a normal inhalation to about there, but I've got a lot of room left, right? That room that's left, that is like my residual volume. So there's two parts to the residual volume, right? There's the inspiratory residual volume, which would be the amount of space that's left to inhale. And then there's the expiratory reserve, which is the amount of space that's left in order to exhale. And then there's your vital capacity, which we don't really use vital capacity that often, but that's the maximum amount in versus the maximum amount out, okay? So you can measure these things using a machine, but this is basically what they look like, right? Here's normal breathing. And then maybe somebody takes a really big breath in, they can't breathe any more than that. That's their inspiratory reserve. And then if they exhale as much as they can, that's their expiratory reserve, right? So that area from there to there is what we call the vital capacity. So normal, quiet breathing, vital capacity, right? And then there is like a little bit of residual volume there just because like none of us can really contract, in the same way that like if you were to crumple up a sack, it's like, yeah, but there's still a little bit of microscopic space in there, right? That's the residual capacity. It's like the amount of space that just happens to be left. Even if you're like, you're trying to breathe it all out, there's still just a little bit, so those are that's what we talk about. Honestly, guys, I don't think you'll be tested on this too much. The only one I'd say get familiar with is the term tidal volume. I have seen that question before. Maybe it's even in today's homework actually, but tidal volume, normal, quiet breathing, right? Now, talking about like this gas exchange, we've already talked about it a little bit, right? One of the things that's really important is to understand that like this gas exchange has to happen because of two types of gradients, right? Stuff will always move down concentration gradients or down pressure gradients. So there's two types of gradients that we're talking about here, right? Areas of high something versus an area of low something, right? So gas exchange requires a pressure gradient, right? Again, this is totally me talking here, but you can see nature hates gradients, right? And so we'll always move oxygen or other gases down their concentration gradients from an area where there's a lot of pressure to an area where there's very little pressure. So, you know, the reason that oxygen is leaving the lungs, if we look at like gradient of lungs external gas exchange, that's at the body's tissues. I need the at the lungs. It's not bad. This picture is actually what I want. I just need it in reverse. Oh, actually, you know what? No, they're right next to each other. Boop, boop. Okay. So you can see here, inside of this blood cell, there's a lot of CO2 and there's very, very, very little oxygen. So because of that, oxygen, which there is a lot of in the lungs, is going to naturally move this way, right? Because nature wants it to move from an area where there's a lot of it to an area where there's very little of it. And the exact opposite is true in your body's tissues, right? Here's your tissues here. Now there's a lot of CO2 and very little oxygen. There's lots of oxygen over here. So oxygen is naturally going to move into the body's tissues. That is a concentration gradient, right? But there is also like, you know, so that's what we're seeing like here, right? So you'll notice, right, there's very little red, there's no red stuff on this side. Let's say that that's oxygen, right? But there's a lot of oxygen over here. That oxygen is naturally going to move this way, okay? Not all of it, right? Obviously, there's still some left over here. It's going to move to where it gets to like even, right? So that is, you know, a concentration gradient where there's just lots of something versus little something. So during external gas exchange, oxygen leaves the lungs, it leaves the alveoli, and it enters into our capillaries because it's moving down its concentration gradient. Meanwhile, CO2 is doing the exact same thing, just in reverse. It's like, you know, nature's looking at it, it's like, wow, there's a lot of CO2 in that blood cell, and there's not very much CO2 over here in the lungs, right? And so it moves it in the exact opposite. So during external gas exchange, at the lungs, basically, oxygen's entering the blood cells and CO2 is leaving the blood cells, which means that oxygen's leaving the lungs and CO2 is entering the lungs. That's why we always say we breathe in oxygen and we exhale CO2. Now, the exact opposite is true at an internal level. During internal gas exchange, oxygen is leaving the blood cells, right, and entering our body's tissues where there's very little oxygen currently. Meanwhile, at the tissues, there was a lot of CO2. So the CO2 is going to leave the body's tissues and get into the blood cell, and the oxygen is going to leave the blood cell. So again, it's the exact opposite, right? It's internal gas exchange versus external. You can see the picture here, right? Here are CO2 molecules, which are the red with the little black one tied to it. And then here's oxygen where it's just the double red, right? So this is why there's the carbon plus the oxygen. This is just the oxygen. So this is O2, this is CO2, right? And so what's happening is here's the lungs on this side, and here's a red blood cell in maybe sitting in the capillaries of the alveoli, right? So the oxygen is going to go this way, and the CO2 is going to go this way. And then when we get to the body's tissues, you can see like here's a capillary bed covering, I don't know, our liver or something. Oxygen is going to leave the blood cells into the liver, and CO2 is going to leave the liver and get into the blood cells. Questions there, guys? That's our gas exchanges. Any questions about how that works? All right, so how does all this happen? Why do our blood cells actually carry all this stuff? Well, your blood cells are able to transport this because they have a special protein inside of them called hemoglobin. So hemoglobin is a specialized protein found in red blood cells that contains a molecule of iron, and iron is what binds to oxygen. So here's the thing, oxygen and iron, they get along together really, really well. But if we look at like oxygenated iron, what happens? It turns bright red. This is why your blood cells are red. You know, look at those new pictures of Mars. We got all these new fun pictures, right? Look at how red the soil is in Mars. There is actually very high concentrations of iron in Mars's soil. That's why it's the red planet. We actually see like higher concentrations there, but there is some oxygen on Mars. You know, it's not, make no mistake, like people, you know, people are like, there's no air. There's some air, which is why like this is a brightish red color, because when iron binds to oxygen, it turns oxygen bright, bright, bright red. So that's why your red blood cells are actually red. Not every animal uses iron, by the way. There is like copper, oxygenated copper, right? And you can see what happens if you put a bunch of oxygen on copper. It turns it this sort of bluish, kind of teal color, right? And you'll see that. You know, humans, we've got red blood cells, right? Because we use the protein hemoglobin. But spiders, crustaceans, certain mollusks, octopuses, squids, they actually use what's called hemocyanin, which is a blue, they use copper to bind oxygen inside their body. There are some out there that actually use green, like chloroform, kind of similar to the way plants do. And then there's even like violet in here. Certain types of worms, the funniest named of which is the literal penis worm, which does have purple blood. So that is, you know, you can see different colors of blood that are out there because they all use different like metals to bind to their blood cells, you know? So we use iron, which is, you know, we use what's called hemoglobin. So when you look at hemoglobin, it actually kind of looks like this. It's this little protein that has like 4 little chains on it, 4 separate like little amino acids, and they all have like a molecule of iron at the center of them. And that hemoglobin molecule is what sits on your blood cells and attracts the oxygen molecules over. Okay, so hemoglobin is this protein that that's found in our red blood cells. It has iron in it, and iron is what attracts the oxygen molecules. So that's why your red blood cells attract oxygen molecules. They also do attract carbon dioxide molecules as well, because carbon dioxide has oxygen molecules in it. But carbon dioxide is transported a little bit differently. Some of it's going to be dissolved in like your blood's plasma. So some of it will be dissolved in like the fluid there. Some of it will be combined with hemoglobin and stuff. And then some of it is going to be converted into what is called bicarbonate, which again is going to be transported by your blood cells. So that's all of the main structure of your respiratory system and all the kind of anatomy there. Now, just looking at like how we control our breathing and stuff. Remember, your breathing is part of it is an autonomic process. Like, yeah, I know that all of us can go and purposefully breathe in, but you actually are using secondary respiratory muscles. You're using somatic muscles in order to allow that to happen. You cannot like have perfect control over your diaphragm consciously the same way that you can with your skeletal muscles. It just doesn't quite work the same way. So it is controlled by your autonomic nervous system, but it is what we call semi-somatic or semi-autonomic, if you want to think of it that way. Where, yeah, it is possible to change your breathing rate consciously, right? I can slow my breathing rate down. I can speed my breathing rate up if I choose to. But at the same time, if my blood starts to get really acidic, you know, if there's like a lot of lactic acid running through my blood or other materials, or adrenaline, things like that, what will happen is like when I modify my blood's chemistry like that, the autonomic parts of my brain will cause me to start breathing a little bit faster, right? Even if I'm not doing any like intense physical activity, which is what you experience when you see people who are going through like hyperventilation. When you have people who are like having like a panic attack and they're hyperventilating, what has happened is basically the parts of their brain that were autonomic caused them to, it started making like adrenaline and stress hormones and things like that. Those stress hormones started speeding up the breathing. But here's the thing. It started speeding up the breathing because, like, why do we originally create stress hormones? You know, remember, we're a cave person. At the end of the day, like, we are all still like cave people, you know? So cave people didn't have to get up on stage and talk to an audience of people and get nervous, you know? There was no social anxieties. There was, you know, the only reason to like amp up your breathing was to fight saber-toothed tigers and things like that, right? When we look at like how this, you know, this adrenaline, these stress hormones start increasing our breathing, what ends up happening is our body goes into, you know, these short, shallow breaths in order to vent carbon dioxide out of our body, because carbon dioxide is the byproduct of physical labor, right? So your brain thinks that you're fighting like a tiger or something, when in reality you're just maybe talking to like a group of people, and so you start getting really nervous. And then because you're venting so much CO2, you end up getting rid of so much of that CO2 that then your body is starting to panic because it's like, hey, I need to have some CO2. CO2 actually helps oxygen be driven. It creates that gradient. So your body starts trying to breathe even harder until eventually you are having, you know, a traditional panic attack, which is why what you should do when you are having a panic attack is breathe into a paper sac and then rebreathe. So you breathe into that paper sac and bring that back in, because what happens is you vent some CO2, but then you are not allowing that CO2 to escape the sac. So then you end up reintroducing it back to your body. Then you vent more CO2, but the levels are much higher because most of what you breathed in was CO2. And so eventually you restore the CO2 levels back in your body, which makes oxygen have its ability to bind again. And that's why breathing into a paper bag fixes a panic attack. So, you know, if anybody in here has ever experienced a panic attack before, or if you've ever been around someone who has a panic attack, you know, one of the things that you can do is just help them breathe in their CO2. If they can handle it, there is holding your breath, which can also like raise your CO2 levels, because then you can stop venting it. But good luck trying to get somebody who's hyperventilating to stop breathing so hard, because they're in full panic mode because their autonomic fight or flight system is freaking out. So all that is under the control of your nervous system, right? And here's the part of it where it's happening. It's controlled by these different parts of your medulla, where it basically activates the panic parts of your brain, which we're glad for, by the way. I mean, that's why you start breathing more when you're exercising, you know? You start doing physical work and your body goes, whoo, that blood's getting acidic. We need more oxygen, right? And so it starts picking up your breathing levels. But we do not want to get to a level where we become what is called hypocapnic, where basically you are running out of CO2. And this is what we're talking about that, right? I kind of got ahead of the slides a little bit. So that's hyperventilation. There's also hypoventilation, which is exactly the opposite of that, by the way. Hypoventilation is where you don't breathe enough, which means there's insufficient oxygen, and that's more dangerous than hyperventilation, because, you know, oxygen needs to be able to get into your body's cells. So we don't want to do that either. But those are the different structures of our respiratory system. That's a little bit about the anatomy, a little bit about the physiology. Any questions, guys? You guys feeling good?
Yeah, Brad. So the exaggeration about people exercising with the mask on and saying people are hyperventilating and passing out and stuff because of the CO2 intake, that was bull, right?
Bull crap. So here's the thing. So here's the thing about like the oxygen masks, right? So it's kind of hard to explain. Remember, there's two different types of gradients, right? There's a pressure gradient and there's a concentration gradient. Concentration gradient is the concentration of oxygen molecules in an area. So I'm gonna make my own chart here because I have no idea how to Google this. So let's look at two different scenarios here, right? Here's my first picture, and here I'll put my second picture. So this first one is a concentration gradient, and this one is a pressure gradient. Okay, So now what I'm going to do is I'm going to divide this in half here. So this is a semi-permeable membrane, right? It's a wall. And now I'm going to put some oxygen molecules in here. We'll draw oxygen in red. Ooh, I need a much bigger brush than that. I need a bigger. There we go. $13, $14, $15. Okay, so here is our concentration gradient, right? I've got 16, 17, 18, 19. We'll go 20. So I got 20 dots over here. And over here, I've got 10 dots. So there is a higher concentration over here and a lower concentration over here. So what's going to happen is it will naturally move this way, right? Thanks to the concentration gradient. Now, a pressure gradient is where there is literally less space available, right, for the same amount of stuff. So let's say I want to divide, I guess that needs to be in black here. I'm going to divide this down, right, and we are going to eliminate all this. This is no longer available to us, but I got to get 20 dots in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's the thing. This is a ratio of 20 to 10. And this is also a ratio of 20 to 10. So the concentration of both of these is exactly the same, which means that oxygen is going to move exactly the same. Now, the pressure gradient is different, which means this is going to limit the amount of gas coming in, but it is not changing the amount of oxygen coming in, which is where they sell, you know, they sell those VO2, like they sell, not VO2, but they sell those like elevation masks. You see these, you know, these have been sold for years now, right? And they're these masks, yeah, Marshawn. They're these masks that have these little valves on them. And what that does is that limits the amount of gas that can enter. You know, it's basically, picture this like a mask. Have you guys like gone for a jog or a walk or a hike or anything with your masks on and gotten like sweaty? We wear masks when we play Ultimate and stuff. So like, you know, my mask will get so nasty by the end. It's just soaked in sweat, you know, by the end of the day, which is really gross. But because there's like now fluid covering the linings, it does get hard to breathe sometimes. It gets hard to like draw gas into the lungs. So people might feel psychologically like they're having trouble breathing. But look, the concentration gradient is exactly the same. So it is not difficult for oxygen to move into your lungs. It moves in at exactly the same rate. Your mask does not keep you from being able to get oxygen into your bloodstream any differently than if you were not wearing the mask. They're literally identical. It does feel different though, because the volume of gas that you're drawing into your lungs, it is a harder contraction that you have to make, because like you have to suck air through this thing that's covering your mouth. So psychologically, it feels more difficult, but it does not limit the amount of oxygen that enters your bloodstream at all, because nobody actually absorbs all of the oxygen that goes in. We like to, you know, I just got done describing like oxygen goes in, CO2 comes out, right? That's a very simple explanation. The reality is oxygen goes in and like some CO2 comes out, but some of it got left in the blood cell. Some of the oxygen didn't get into your bloodstream. You didn't diffuse all of it. There's so much extra that was like left over that gets exhaled out of your lungs. We just we don't describe it that way because it's more technical. Does that make sense though? Is able to kind of make that clear?
Yeah, thank you.
Mm-hmm. Now, this is totally not true if you were to go to like Mount Everest, by the way. If you were to like go on top of like Mount Everest, you need to bring oxygen tanks with you because oxygen is heavier than these other gases. Um, and so the further you get away from sea level, the concentration becomes less. And so the concentration inside of your lungs versus outside your lungs might be equal to each other, which means there's no gradient, which means oxygen won't move into your lungs. So going on top of like a mountain, the reason it feels like you can't freaking breathe is, yeah, there's literally less oxygen molecules up there. The amount of gas is actually somewhat similar. But if we look at like the composition of air at sea level versus at Mount Everest, you can see here, that's a great picture. There's our oxygen molecules, right? So, you know, if I divide this, right, I'm just going to copy this image and go to paint here. You know, if I divided this into little sections here, you can see the concentration here is a ratio of 1, 2, 3, 4, 5, 6, 7 versus whatever it is in your lungs. And down here, it's 3. And up here, it's 2. That's not very much, right? There's just not a lot of oxygen available up on Mount Everest, you know, which is why there you need to bring oxygen tanks with you in order to like reintroduce that, right? So, you know, here's a normal pie chart of oxygen concentrations, right? About 21% oxygen, most of it's nitrogen. But at Mount Everest, this pie chart would be much smaller. And that's why those elevation masks do not work. You know, I know I love my guy Marshawn, but here's the thing. I won't say that they don't do anything for you. Those oxygen masks can help build like mental toughness. And so if you are using them to like, you know, strengthen your mental toughness to breathe and stuff, you can get some benefits from them. Because it basically feels like you're wearing 3 or 4 of these, you know, all at the same time. And then it's like, it's just hard to breathe in. So and it may strengthen your diaphragm. So it could have like positive benefits, but to call them elevation masks is totally faulty marketing. They do not simulate elevation. You can't simulate elevation without very intense specialized equipment. All right. So let's take a look at the cardiorespiratory system. So we did the cardiovascular system yesterday. We just got done doing the respiratory system. Let's put them together and look at chapter 3 in your NASM textbook, the cardiorespiratory system. So the purpose of this lesson is to understand the fundamental knowledge of the cardiorespiratory system, shocker of the year. What we want to be able to do is we want to be able to explain the different components of the cardiovascular system, the different components of the respiratory system, and how those two systems work together to be their own system, which is the cardiorespiratory side of things. We'll also talk about how that relates to human movement. You know, this is what gives us the ability to generate energy and do stuff. And we'll talk about how that energy expenditure is related to dysfunctional breathing patterns as well, and how dysfunctional breathing can really screw everything up. So your cardiorespiratory system, by definition, is, we call it a support system, you know, because it supports the kinetic chain's ability to move in the body, and it is responsible for providing tissues of the human movement system with oxygen, nutrients, protective agents, that's your immune system, and a means by which to remove waste products. So it's how we get rid of CO2. And so it consists of our cardiovascular system and our respiratory system. So the cardiovascular system side of things, this is going to be your heart, blood, and blood vessels, just like we said yesterday. When we talk about the heart, it is a muscular pump that is designed to push blood throughout the body. And so it has all these really cool cardiac fibers, and those cardiac fibers are specially designed to rhythmically contract and generate, again, pressure, right? This time it's fluid pressure or blood pressure, right? And so the typical, heart rate that we're going to see is about 70 to 80 beats per minute, depending on who you ask. That's the typical rhythm of a heart rate. Obviously, some people in here, everybody in this call right now, everybody watching this video, we're all studying to be personal trainers, fit people, right? So chances are you've noticed that your resting heart rate may be below 70 or 80 beats per minute. That's great. That's awesome. But our typical heart rate is between 70 and 8. Like I'm being pretty animated right now, not really in a resting state. And, my heart rate's right at 70, at least according to, these faulty things. But that's the average internal rhythm that we're going to see there. So, we do control this heart rate using a specialized, what we call a conduction system. You can see a picture of that right here, right? And so this conduction system, these wires basically that are running through your heart, are these specialized structures that generate and control your heart's internal rhythm. And so it's all under the control of this little material right here that lives inside of this right atrium called your SA node, or your sinoatrial node. This is the actual pacemaker of the heart, right? And this determines your heart's rhythm. So that sinoatrial node, that pacemaker, is what sets how often your heart generates electric signals in order to contract. So the SA node is going to be tied to what is called your AV node. And the AV node is this little, it's called the atrioventricular node. And so this will initiate the signal, but this will delay the signal for just a second. So when that signal gets initiated, it will contract along this wire here and this wire up here, and that allows the top of the heart to contract. But this delays the signal for a second, and then it continues traveling after the delay is over, and that allows the bottom of the heart to contract, which you can see there's a lot more wires here. This is you're going to have what's called your bundle of His over here, and then that's going to branch out into what are called your Purkinje fibers. Those Purkinje fibers run throughout this very muscular part of your heart, and the bottom of the heart is make no mistake, much, much, much more muscular than the top of the heart. And so this is where the second, the ventricles are contracting to eject blood out of the heart. So, that rhythm, that 70 to 80 beats per minute, it is set by that SA node, and then it's controlled by the rest of your conduction system. So looking at the heart and looking at the chambers of the heart, right? Remember, its job is to generate and maintain blood pressure, right? You've got different chambers here. And so those chambers are going to create these areas of high pressure and these areas of low pressure. And so you've got the gathering chambers, which are called your atria. These chambers gather blood as it is returning to the heart. So you've got the right atrium and the left atrium. The right atrium is going to gather low oxygen blood. This is where the SA node lives, right about here. And so this is going to gather a lot of blood in that right atrium as it is returning from the body. So since it's returned from the body, that means that it dropped off all of its oxygen. It's low oxygen blood. The left atrium is gathering blood as it returns from the lungs. So that is very high oxygen blood. Then both of those atriums are going to drop that blood into their lower chambers here, which are called your ventricles. And ventricles are chambers that pump blood away from the heart. So you've got your right ventricle and your left ventricle. Remember, the right atrium gathered oxygen, low oxygen blood that returned from the body. So when it drops into the right ventricle, it's going to contract that out of the heart into the lungs so that it can go pick up some oxygen. So the right ventricle pushes low oxygen blood into the lungs, and the left ventricle pushes high oxygen blood out through the rest of the body. So you can see we laid this out differently today, guys. Yesterday I laid it out left side of the heart, right side of the heart. Today, we kind of laid it out like tops up part of the heart, bottom part of the heart. So it's just a little bit of a different way to study it. I don't know which version you're going to prefer. But again, my biggest piece of advice to you when trying to memorize the heart, memorize the left ventricle first. This is the part that pushes blood throughout the whole body. And as long as you remember that, you can be like, all right, well, if that pushes blood out to the body, then the right side must push blood to the lungs. And if you remember that these both push blood out, you can remember that these both gather blood in. And so you can kind of, logic square, crossword puzzle, memorizing your different chambers of the heart there. Any questions on that? I know the chambers are just free questions, free points on a test if you can memorize them. So I always like to ask. Okay, so let's look at the function of the heart here. So how do we measure like the heart's function? Well, we're going to be measuring the volume of how much blood your heart can beat per minute, right? In the same way that like, my overall traveling speed would be the function of like how many steps I can take per minute times how much distance I am covering per step. The overall function of your heart is a measurement of how much blood you can pump per minute. So that's number of times your heart is beating per minute times the amount of blood ejected per beat. And so that's where we look at these two different sections, where we look at the measuring your heart's function. You're going to have your stroke volume, which is the volume of blood pushed out of the heart per beat. And then you're going to have your heart rate, which is the number of times your heart beats per minute. So both of those things come together to make up what we call your cardiac output. That's the overall performance of the heart. And it is, how much blood is pumped per minute. So we look at that as cardiac output equals stroke volume multiplied by heart rate. Now, you want to keep an eye on heart rate because we can't really measure stroke volume. We can just draw on the assumptions. If your heart rate's really high, chances are your stroke volume is relatively low. So the way that NASM prefers to tell you guys to like measure your pulse rate is to use what is called your radial pulse. And your radial pulse, what you're going to do is you're going to locate your radial artery, which is running down your wrist here, by using two fingers in line with your thumb and index finger just above the wrist. So I go just above my wrist, actually right where my freaking watch is at. I go just above my wrist, and I'm in line with my thumb and my index finger right where those two come together. I place two fingers right there, and sure enough, that I can feel my pulse, right? Right. Now, I will say, if your client's like flexing their hand back like this or really intensely flexing it this way, these ligaments that are in your wrist there can get in the way. So if that is the case, you may need to like get pretty familiar with how to kind of like hold that in just the right spot. It does take practice. I really recommend that everybody kind of practices measuring this. I know we live in a world today where it's like heart rate monitors or $20 off eBay. That's an exaggeration, but I always recommend it's a good idea to be able to test it manually. And what the NASM recommends is basically if you're trying to figure out what your heart rate is in this moment, NASM recommends measuring it for 6 seconds, and then you can just add a 0. So, if I go like this, and then I have like a stopwatch, I would just measure it for 6 seconds. 1, 2, 3, 4, 5, 6, about 7. And sure enough, it's going to come out to about, I'm going to add a 0 to that. So it'll be between 60 and 70 beats. And that works really well, like when you're exercising. If you're trying to get into your heart rate zones, just measuring that generally is a really good way to do it. But if you do have a heart rate monitor, they're great. It's a great way to make sure. Now, remember, this method here works really well for getting your heart rate in real time if you need it that second. But if you're trying to get like a resting heart rate, I recommend actually measuring it for a full 60 seconds while your client is like sitting there relaxing. And then if you're getting like a recovery pulse, you need to measure the recovery pulse for as long as prescribed by whatever assessment. Like in the YMCA step test, you need to do it for a full 60 seconds. Do not get it for 6 seconds and multiply by 10. That will give you a totally inaccurate reading. The test is about how quickly their heart rate returns to normal. It's not about what their heart rate is at the end of the test. Next part of your cardiovascular system is blood. Blood is going to act as the medium to deliver all these, essential nutrients, right? So blood transports oxygen, it transports hormones, glucose, waste products, all this different stuff that's running through your body. You get about 5 liters of blood. That's about 1.5 gallons overall at any given time, depending on, your body fluid levels and body size and things like that. But generally, it's about 1.5 gallons, which is not very much, by the way. You think about it, it's not that much blood in your body. But inside of your blood are red blood cells, right? And red blood cells, which are known as erythrocytes, are specialized cells that contain hemoglobin. And hemoglobin is that protein inside of your blood that binds to oxygen and allows for the transportation of gases. So blood actually kind of looks like this. If you actually look at blood, give me a pie chart. This is actually kind of what you're going to find in your blood. That's not what I want. There we go. No, that's not what I want either. Not blood types. Does that say 36% of people are type O? Bull crap. No way. This has got to be like a special case, like a special population. Most people are type A. Talking about blood. Oh man, I'm just not gonna find the chart I need. There we go. Good God. So most of your blood is plasma. That's basically just like the fluids within your blood and other materials being suspended in it. Some of it is platelets, very little actually. There's your red blood cells, about 40%, and then your white blood cells are about 1% of your blood. So that's what blood actually looks like. If you spin your blood really, really fast, it'll actually kind of look like this. You'll see there's your plasma, there's your red blood cells, different proteins that are just kind of in the blood, white blood cells, and platelets and stuff. So you're going to find, sugar and fats and minerals and vitamins and all this stuff running through your blood, in addition to, just the hemoglobin and stuff. Now, we've also got our blood vessels, right? And this is the third component of our cardiovascular system. This is where all those blood cells are going to travel. Our heart's got to be able to splash blood all the way down to the feet. It can't really do that if it were to literally just splash it down there. So luckily, it's connected to a series of closed tubes. Those closed tubes are your blood vessels. So your blood vessels, or your circulatory system, is a closed circuit of hollow tubes that allow blood to be transported to the various parts of the body and back to the heart. So you have got 3 main types of blood vessels here. You're going to have arteries, which are carrying blood away from the heart. You're going to have veins, which are carrying blood back towards the heart. And then we're going to have capillaries, which are acting as like the exchange sites for different materials. And they are covering our tissues in these little capillary beds there. So that's your cardiovascular system in a nutshell. I know that's pretty much everything that we said the other night, but you'll notice like all of it made its way onto the notes. That's because, like, again, think of the NASM slides, guys, as like a filter. Everything that is on this page of notes is likely the most important stuff that will be on your real NASM test. So some stuff didn't make it on here. I would say, and I'm no, I'm an expert, but I'm not like, I don't know perfectly. I don't have the test memorized or anything. I'd say you're pretty good to basically focus on the stuff that's mostly on these note pages here. So looking at your respiratory system, this is the second functional component of the cardio cardiorespiratory system, right? And this system works very intimately with your cardiovascular system. This provides a means by which to collect oxygen from the environment and deliver that oxygen to the bloodstream so that it can be transported by the cardiovascular system. So it allows for proper cellular function. That sentence is always really, really important. And it's made up of two different divisions, your respiratory pump and your respiratory passageways, okay? So you can see the respiratory passageways here, and then we'll look at the respiratory pump first, though. So your respiratory pump, which is located in your thoracic cavity, it's located in your rib cage, it provides the framework and the flexibility for the expansion and compression of your lungs. It allows for ventilation. Remember, ventilation is different from respiration. Ventilation is drawing gases into the lungs. Respiration is the process of exchanging those gases. So this is going to consist of your bones, like your sternum, ribs, and vertebrae. That's part of the respiratory pump. You know, your ribs are heavy, them resting back down to drive air out of your lungs. That's pumping air out of your lungs, right? But we've got muscles like your diaphragm, which contracts. We've got muscles like your scalenes on the side of your neck, your intercostal muscles between your ribs, your sternocleidomastoid, your pec minor, you know, your abdominals even. Those little muscles there are going to assist in breathing a little bit. But we got to remember that they are what we call secondary respiratory muscles. And unfortunately, those scalenes, the sternocleidomastoid, the pec minor especially, and the abdominals, these are all also skeletal muscle. These muscles also move our body and do all this stuff. So because of that, because these muscles don't only help with breathing, they also help with posture. When you get overactive posture, it screws up your breathing. And that is why we see like people who have like who are likely to hyperventilate are the same types of people who breathe like this, right? Rather than breathing from their diaphragm. So you start relying on secondary respiratory muscles instead of the primary respiratory muscles, primary one being your diaphragm. It also will end up altering your posture. And then all of a sudden we end up with rounded shoulders with tight pec minors. We end up with a forward head posture with tight scalenes and sternocleidomastoid. We end up with elevated shoulders with tight traps, right? All these extra muscles that really we shouldn't have, overdeveloped, but they screw up our posture, right? So that is those are the muscles of your respiratory pump. And like I said, they do have like postural distortions associated with them. So we also have our respiratory passageways, which your respiratory passageways are basically the passageways that allow air to travel into this, oxygenated environment. So your passageways are going to be like your larynx, your pharynx, your trachea, and then the bronchi, and then the tiny bronchioles, which end in the alveoli, which end in the alveoli sacs, right? And that is where, those little passageways there are going to be covered in blood vessels, right? So, the passageways that funnel air into and out of the lungs, they're the tubes basically. And they've got those alveoli and alveolar sacs, those little popcorn sacs that are covered in blood vessels, allowing for O2 to work its way across from one side to the other and get into the bloodstream. So we've also got to look at, the overall way that these two systems actually work together. And that is where the cardiorespiratory system comes in. So when we're looking at the respiratory system, right, your respiratory system's job, we look at the cardiorespiratory system, your respiratory system's half of it is provide a means by which to gather oxygen. And the cardiovascular system is going to transport that oxygen. So we need to be able to measure what the typical oxygen utilization is inside like the regular human body. And it's going to be about 3.5 milliliters of oxygen for every kilogram of body weight per minute. Okay, that is known as a metabolic equivalent or a MET. You've seen METs on treadmills, right? we see like met. So when you look at charts like this, you look at a chart like this, you'll notice that like sweeping the carpet, and that's a picture of a vacuum. Huh. When you look at, also, who sweeps carpet? When you look right here, right? Like this is going to burn about 100 calories an hour if you do it for 30 minutes, right? Or no, sorry, about 100 calories in 30 minutes, right? So this is a MET of about 3.3 METs. So if a metabolic equivalent is that we as humans consume about 3.5 milliliters of oxygen for every kilogram of body weight per minute, right? So I weigh about 78 kilograms times 3.5. So I consume about 273 milliliters of oxygen per minute when my body is at rest. So if you were to, this is like a 80s comedy. If you were to like kidnap me, and I was asleep the whole time, right? Like you don't wake me up, so my body just stays asleep, and you were to put me in a coffin with, let's see here, 273 times 30. If you were to put me in a coffin with 8,190 milliliters of oxygen, I would be able to breathe for about 30 minutes. I'd have about 30 minutes worth of air. But obviously we're not at rest, right? We're constantly like doing stuff all day. So we are in some blend of like, how many METs we're using. Sweeping the carpet with a vacuum cleaner it puts you at about 3.3 METs. So you'd be consuming about 3.3 times as much oxygen as you would if you were just like totally asleep. Gardening, you're consuming about 4 times as much oxygen. You're playing with the dog, it's about 4 times as much oxygen. Playing with the kids vigorously, it's about 5 times as much oxygen, and moving furniture is about 6. So that is what a MET is. You can see like here's playing soccer, it's about 10 times as much oxygen. So there's a lot of oxygen consumption here, which means that you need to make sure you have a system that will support driving in that much oxygen, but also like delivering it. And so that is what a MET is. Now, I like METs. I like to describe it to my clients. I think they're really fun to like motivate yourself. It's like, hey, you burned 4 times as many calories as you would have if you were at home sitting on the couch right now. It's like, yeah, that is exciting, right? But METs are kind of hard to like calculate directly without like, measuring how much someone is breathing. So I'm not a huge fan of the MET system, but I do think it's kind of a fun way to kind of lay it out to your clients. You're probably going to be tested on this. What you need to remember is the only version of the question I've ever seen is they'll say, what is the average resting oxygen consumption or metabolic equivalent of adults? And you need to remember that it's 3.5 milliliters of oxygen per kilogram of body weight per minute. That is 1 MET. And we are all, when we're at rest, at 1 MET. So last thing we want to talk about is how the heck we can screw all this up. So we obviously do have dysfunctional breathing patterns sometimes. Like I said, it's very easy for us to, maybe through our posture, alter our breathing patterns. And so dysfunctional breathing in the cardiorespiratory system can directly impact the components of the human movement system. So basically, like by dysfunctionally breathing, you can mess up your posture. But the reverse is also true. If you mess up your posture, it can mess up your breathing. So that can lead to further dysfunction of the kinetic chain. So improper breathing patterns can totally affect your posture, and your posture can affect your breathing patterns. This is one of the biggest reasons why we need to make sure that we encourage our clients to breathe while they are exercising, but we also need to encourage that they are, in an upright position with shoulders rolled back and chin ever so slightly tucked. This is my posture that makes it easy for me to breathe properly. If I'm like this, that closes down my diaphragm, and causes me to rely on secondary respiratory muscles. So I end up having shallow breathing patterns, which means that my abdominals, my sternocleidomastoid, all these other muscles are used instead. That can lead to shortness of breath, and it can lead to headaches, nausea, too much CO2 being in the body, which causes stress. So you start to get these like back of the head tension headaches. Not to mention it screws up how your scapula moves, which means like you can end up with shoulder impingement, and lots of other problems as well. You wouldn't think that breathing would be tied to our posture, but it is a direct component of it. And that is the cardiorespiratory system. So you'll notice we put a lot of the same information in here, but that is because, like I said, like that's the NASM filter, right? Sochi's giving you a lot more info than you're going to be tested on, because we want you guys to be advanced, not just a basic trainer. But for the purposes of passing your test, this half of the notes down here is going to be very, very helpful. So summarizing everything up, the respiratory system gets oxygen from the environment through your nose and your mouth, and then makes that oxygen available to your bloodstream. So then it passes into your bloodstream so that your cardiovascular system can deliver it to your body's cells. So as your cells use that oxygen up, they are exhaling the byproduct in the form of CO2. And we got to get that crap out of our body. So our cardiovascular system is going to get it back to the lungs so that we can exhale that CO2 away. And the collection of this is made possible by your respiratory pump, which creates a pressure gradient to draw massive amounts of air into our lungs, most of which is nitrogen, but there's a lot of oxygen in there. Or it relaxes to drive that CO2 out of our lungs, right? And if there is dysfunction in the cardiorespiratory system, that can directly impact the components of what we spend most of our time talking about, which is the human movement system. Your cardiorespiratory system experiencing dysfunction can screw up your posture and ability to move properly. And that is about everything I got for you guys today. Questions, comments, concerns? Dalen, Andres, Kenny, what do you
got? No questions.
Good.
Alrighty, fellas. Well, if that's all you got, don't forget homework 3 is up. I was almost at homework 2. Homework 3 is up today, up on Canvas. So please try to get that done. If you have any backlogged homework, you should have gotten an email from me yesterday detailing what assignments I am missing from you. So please get your butts on the Canvas and knock them out. Those are going to be all posted on Monday. Also, one thing I said in the email, and if you were looking at some of your scores and you're like, hey, like, man, if he goes and posts these grades, I might end up with like a B in the class, but I really want to have an A. Go take your homeworks again. Raise the average, guys. Every time you get 100, the average goes up. So just practice them over and over and over and over again. I know that seems like schemy. You're like, I know the answers. I could just write them down and take it over, and just push them in over and over and over again. Here's the thing, guys. That's called studying. You deserve to have the scores raised for doing it. It's not taking it's taking advantage of the system, but like you're benefiting from it. Like that's not cheating. That's awesome. So raise your averages. Go kick some butt today. And you guys have a freaking great weekend, and I'll see you on Monday. We got some great weather this weekend, guys. Take advantage of it.
You too.
See you later.